All right, we've talked about linear transformations in general, and now we're going to talk about a particular type of linear transformation called injective linear transformation. Here, let me turn this on here. Okay. And actually, we're going to talk both about injective and non-injective. And in some sense, the non-injective are more interesting than the injective. And we're going to relate this to various things that we've talked about, like null space, linear independence, and so on. All right, so here's the definition of an injective linear transformation. Suppose T is a linear transformation. All right, we know that it has the linear properties. Basically, that means that T of alpha 1 U1 plus alpha 2 U2. The linearity property says that's the same thing as alpha 1 T of U1 plus alpha 2 T of U2. So that's the injective property. I'm sorry, that's the linear transformation property. Now, linear transformation is injective whenever T of x equal to T of y implies x is equal to y. So if the two images are different, then the two sources are different. Alternatively, we could say that x is unequal to y implies T of x is unequal to T of y. That's an alternative specification. This is called the contrapositive of this assertion. Two different inputs go to two different outputs. Now, if you have had a discrete math class, you probably have seen this term one-to-one. That's exactly what we're talking about. Injective means that the linear transformation is one-to-one. All right, now let's consider some examples. Here's a linear transformation defined by its action on the vector x1 through x5. So in fact, this takes vectors in C5 to vectors in C5. And it turns out that if you compute t of this vector, it turns out to be equal to t of this vector. That means you have two different vectors, x and y, that map to the same result, not injective. Okay. Here's a cartoon of a non-injective, okay, because here we have two distinct elements being mapped to the same element. So this is non-injective. Okay, for injective, let's take a look at this mapping. Here's another mapping that's defined by its action on vector. So there's a 5-component vector maps to a 5-component vector. So let's try to prove that it's injective. Okay, so we want to show that if T of x equals T of y, then x equals y. That's what we're going to try to show. T of x equal T of y implies x equal y. Okay. All right, now, if T of x equal to T of y, so let's start with this statement, T of x equal T of y. That means that T of x minus T of y is equal to 0. All right, that's this statement here. So this expresses our hypothesis that T of x is equal to T of y. And what we want to do is start with this hypothesis and end up with the conclusion that x equal to y. That's where we're headed. Start with this hypothesis and show this conclusion. All right, so if we have this, then we can use the linearity property to say that 0 must be equal to T of x minus T of y. And that's, so actually what we're getting here is this is the same thing as, it actually goes through a long process here. We know that this is equal to T of x minus y. So we could have cut to the chase right down here, because this here expresses T of x minus y. Okay, so we know that 0 is equal to T of x minus y. All right, so that means that here we have 0 is equal to this. Now, actually, what we're showing here is the null space of this matrix, right? If we have a solution of this equation, 0 vector equal to a matrix times another vector, that means that this vector here must be in the null space of this matrix A. So we'll call this A. It's in the null space of A. We know very well how to find null spaces. You do a row reduction. When you row reduce this matrix A, it reduces to the identity. So that means that the null space, the dimension of the null space is 0. So that means that the only solution to this system is the solution x1 minus y1 equals 0, x2 minus y2 equals 0, etc., etc., etc. That means that x must be equal to y. Right. So here we can see a very close connection between the notion of injective and the null space of the matrix associated with the linear transformation. In this case, we saw that the null space was trivial, so the linear transformation was injective. And in fact, that's the general case, that when you have a trivial null space, you have an injective linear transformation. Here's a cartoon for an injective linear transformation. Notice these odd men out here. Injective does not mean that every vector in the codomain has a vector in here that goes to it. That's not necessarily the case. We'll reserve that for the next section. Okay, so let's think of another example here. We have a mapping from polynomials of degree 3 to matrices, 2 by 2 matrices. And we can do the same thing. Let's see if this is injective or not. Well, we want to show that if t of one polynomial equals t of another polynomial, does that imply that in fact these two polynomials are the same? Start the same way. If these two are equal, if the two outputs are equal, then we can write that their difference is the 0 matrix. And by linearity, we end up with this result here. That if the difference between the two polynomials, if the difference between the two images is 0, that means that the matrix formed by the differences is going to be 0. We can now write this as a system of equations for the differences a1 minus a2, b1 minus b2, c1 minus c2, d1 minus d2. What we're going to want to show is that all of these differences are 0. So we're treating these as our variables. And again, we're going to want to show that these differences are 0. All right, now here we have a system of linear equations which we can write as a matrix vector equation. Once again, we're trying to show that this matrix vector equation gives me 0 result. Okay, that's again, it's the null space. So we're looking for the null space of this matrix. Okay, now since the matrix is non-singular, it turns out that the null space is trivial. And the only solution is if all of these differences are 0, which means that in fact the two polynomials that have the same image must in fact be the same polynomial. Okay, so you can go through this procedure repeatedly to show that transformation is or is not injective. Okay, now related idea, let's consider the case where the transformation is not injective. When the transformation was not injective, we were able to find, let's back up here. Well, we were able to find two different vectors that map to the same vector. Okay, so we had t of 1, 3, minus 1, 2, 4 is equal to t of 4, 7, 0, 5, 7. In this case, where we had a non-injective linear transformation, we had this being the case. Now, by linearity, I can say that t of the difference of these two vectors, 1, 3, minus 1, 2, 4, minus 4, 7, 0, 5, 7. T of the difference of these two vectors is going to be 0. What does that mean? That means that there's a vector, the difference of these two vectors, this vector, when t is applied to it, gives me 0. All right? So this is called the kernel of the linear transformation. If I have vectors that are mapped to 0, these vectors are said to be in the kernel of linear transformation. And you can see that that's kind of related to the null space of the associated matrix. So let's go back to this definition of kernel. And the kernel of a linear transformation is the set of vectors in the domain U, that are mapped to 0 under the linear transformation. And here's this comment that the kernel of T is just the preimage of 0, T inverse of 0. T inverse of 0 means all the vectors that are mapped to 0. Okay, so let's consider this linear transformation here. We have a linear transformation that maps 3-dimensional vectors to 5-dimensional vectors. And in order to find the kernel, we want to find all the vectors that map to 0. So we can set up this system of equations. Here we have, in fact, a homogeneous system of equations. And we're essentially looking for the null space of the coefficient matrix. Turns out that the null space is non-trivial in this case. We have one free variable. And that means that we have a one-dimensional null space. Okay. And it turns out that the kernel of a linear transformation is a subspace. And you can prove that using these linearity properties, that the sum of two vectors, if each vector gets mapped to 0, then their sum gets mapped to 0. And if a vector gets mapped to 0, then any scalar multiple of that vector gets mapped to 0. So that means that membership in the kernel has this closure under the two linear operations. So that means the kernel is a subspace. Okay, let's consider another linear transformation where you have 3-dimensional vectors mapping to 5-dimensional vectors. To find the kernel, you want to find solutions of this system of equations. Here we have the system of equations. We can write this as a homogeneous system. We have the coefficient matrix. It turns out, in this case, the coefficient matrix does not leave us any free variables. So the null space is 0. The only vector in the kernel is the 0 vector. Okay. All right, now here's a very general and important theorem. We notice that the kernel is equal to T inverse of 0. Now we want to characterize T inverse of an arbitrary vector. It turns out that T inverse of an arbitrary vector is very closely related to the kernel. And here is the relationship. If I take T inverse of any vector in the range, then I can write that as one particular vector in the inverse image plus any vector. This is any vector in the kernel. So I can write it this way, that the inverse image of one particular vector is equal to one particular vector plus the kernel. So this is a set addition. This means that I add this vector to every element in this kernel. And we'll see pictures later on to show what this means. Okay. All right. So to show that two sets are equivalent, we're actually showing that two sets are equivalent. We're showing that T inverse of V can be written as U plus K of T. So we need to show two ways. We need to show that any vector that's in the inverse image of V has this form, and on the other hand, any vector that has this form is in the inverse image. Okay, so let's see how this works. Let's consider first this set here. And well, here, let me clean up some of the garbage here so you can see what's going on. All right, so let me repeat that. You want to show two things. First of all, you want to show that U plus K of T is a subset of T inverse of V. And then you want to show that T inverse of V is a subset of U plus K of T. Now, V is what's given. U is one particular element of T inverse of V. All right, so first let's start with the first one. So let's consider this set, and we want to show that it's contained in T inverse of V. Okay. In other words, we just need to show that every vector in this set maps to V. Now, that's what it means to be in T inverse of V. We want to show every vector in this set maps to V. All right. So let's take W in the set. W has this form U plus Z, and apply T to this. W means I can apply T to this particular form. I use linearity. I know that T of U is 0 is V, and T of Z is 0 because Z is in the kernel. Okay, so we do get, in fact, that any vector of this form maps to V, which means that that W is in T inverse of V. Okay. Now, on the other hand, let's take any x that's in T inverse of V. All right, then you can take T. If you take T of x minus U using linearity properties, you find out that that's 0. So that means that that means that x minus U maps to 0 under T, and that means that x minus U is in the kernel. So if x minus U is in the kernel, that means that x is equal to U plus, x is in U plus K of T. All right, and that's exactly what we wanted to show. All right. Now here's the picture down, there's a picture down here that's illustrative, and I think it's very good to see. Here are all of the vectors in the range. Let's look in particular at 0. Now, if the mapping is not injective, there may be many vectors that map to 0. Now, all of these vectors map to 0, so I can say this slice here is T inverse of 0. All right, now let's consider a different vector here. This different vector also may have many vectors that map to it, and it also corresponds to a slice in your domain. And it turns out that every vector in this slice can be thought of as one particular vector, U2, plus every vector in this 0 slice. So if I take, this is U2 plus 0, this is U2 plus this one, this is U2 plus this one. Every vector in this slice here is equal to a vector in this slice plus U2. And that works for the same way for any possible vector over here and the inverse image of that vector. If you know anything about abstract algebra, these sets here are called cosets. All of these are cosets here. If you hadn't had abstract algebra, you can let that go, but you can remember that. It's a common concept, not just in linear algebra. Okay. All right, now, we noticed that in the case where we had an injective linear transformation, then the only vector that mapped to 0 was 0. So in fact, if you have an injective linear transformation, the kernel is equal to 0. And you can prove that both ways. You need to show if T is injective, then the kernel is simply 0. And if the kernel is simply 0, then T is injective. Okay. All right. But from this picture, you can see that if the mapping is injective, you're only going to have one vector over here. If you only have one vector over here mapping to each one, then you're only going to have one vector mapping to 0. Okay. We have some more examples here. When we have the vector that's not injective. Okay, so I think you can read through these examples. And I'm going to stop here and pick up with the next video.